Okay. I try to record on Screencast-O-Matic, which is not a new package, but it's new for me. I used to use a package called Tegrity, which was really easy to operate. It was fast. It did a good job. It had a lot more features, but the bean counter said it cost too much. So they said we have to use Screencast-O-Matic, which is a cheaper program. I'll just leave it like that. Okay. Now, they told us all we had to do was sign up, and it's free if you do 15 minutes or less. Well, I can't do a class in 15 minutes or less. Well, we'll provide the pro version that gives you unlimited time. Okay, fine. So they provided that. More than 15 minutes. So I recorded those, and that's what's taking up all my memory right now. Is I recorded the first week and stored them on my laptop, and then I tried to load them to Blackboard. Tried to do that Friday and over the weekend. The files were too big. Okay, so I checked with the people. They said, well, dump them to Yahoo and then just do a link to Yahoo. So I had to develop an account and all this kind of stuff. So I was in the process of doing that. I think it was actually Thursday afternoon. And Yahoo has a 15-minute limit. Okay, now wait a minute, What good is having Screencast-O-Matic going unlimited if Yahoo only has a 15-minute? Oh, but you can extend that. So it took me Thursday, it just wouldn't work. Friday, I couldn't get it to, in order to get it extended, you had to have a cell phone, and guess what? I'm the last person in Alabama without a cell phone, so I couldn't do it, so I had to wait till I was home. My wife has a cell phone, so we did it Sunday. And then we started uploading, and things seem to be doing okay, except now I have to get them linked back to Blackboard. And supposedly that's an easy step, but I couldn't do it yesterday afternoon because I let an adjunct instructor use my computer on Monday and Wednesday afternoon. So I will be able to do that hopefully this afternoon. So it's a really convenient program, by the way. All right, anyway, you've heard enough of my sad story. Violin music in the background really was helpful, wasn't it? Okay, so once I can get them, and hopefully that'll be this afternoon, then those who weren't here before or have missed a class, you'll be able to see and hear, hopefully, everything we did once we got Screencast-O-Matic open. Okay? That will be a review of the syllabus where I go over it. It's out there on Blackboard now, but you actually hear me talk about it. Same thing with research paper instructions. It'll be on Screencast-O-Matic or YouTube. Okay, I'm really computer literate. YouTube, you'll be able to hear me talk about it as well as see it, and a locator card, that kind of stuff, and what we did in every class so far. So, anyway, hopefully it'll get loaded today. I sure hope so. Okay. And I've got to clear my memory too. You would think as much as I forget, that wouldn't be a problem, but it seems to be on the computer anyway. Okay, I thought that was a pretty simple thing to view the slides. Here we come. It is slow today. Okay. Now, you think I'm doing something that's worthless now because what you see now and what you see in a minute, you won't tell any difference, but this affects what Screencast-O-Matic records. Okay, now we got it right. All right, no questions on what we've done so far? All right, we're right at the beginning of 1.4. We got started last time. 1.1, 1.2, 1.3. Review those on your own. When you, if you have any questions, please bring them and ask. Okay, we were talking about functions, and just we're beginning to talk about function notation. We talked about some of the characteristics of functions. Now, to help understand this definition, let's go back to the previous page. Here's the definition. A function f, very creative in how they name the functions, f, from a set A to a set B It takes stuff from one thing, operates on it, sends it to another set. Is a relation that assigns to each element X in the original set, A, exactly one element in the output set, B. Okay? The set A is the domain. All the possible inputs are to the domain of the function F, and the set B contains the range, all the possible outputs of that function. Okay? So that's the definition they're talking about. Here's another way to look at it. Now, to understand that, look at the function, but this is called I have a name for this, sort of like a mapping. So right after class, someone said, when we did functions in high school, we did graphs. We're going to get to that, okay? There's a definition, there's mapping, there's graphs, there's ordered pairs, there's lots of ways you can express a function. Here is what we call a mapping, okay? These are the times of the day in the afternoon, 1, 2, 3, 4, 5, 6. So those are your what? Domain. This set of times here is a domain. And what you've got a thermometer out on the tree there, okay? And at 1 o'clock, you're going to check that thermometer and see what the temperature is. Now, sadly, we bought one in Celsius, not in Fahrenheit. So these are Celsius temperatures. And this shows that at 1 o'clock, it was 9 degrees Celsius. Anyone know about what that is? It's a lot cooler than it is here. This is not summer in Alabama, okay? 9 degrees Celsius would be maybe 50 degrees, okay? Okay. At 2 o'clock, it had climbed to 13 degrees Celsius, a little warmer, but that's still not very warm. 3 o'clock, it made it up to 15. At 4 o'clock, it was still 15. Had it stayed there, well, it went up and maybe came back down. At 5 o'clock, it had dropped to 12, and at 6 o'clock, at 10. Now, these are our domain. The range could have been basically any temperature conceivable that you could have recorded, okay? And I don't know what time of the year that was, but that could have been from negative numbers up to 20, maybe even close to 30, okay? I doubt if you ever get close to 30 Celsius, okay? But that would be the range. We didn't use all the range, but everything in here was in the range. The temperatures we measured were in the range. A lot of values we didn't use. This in the case you went 1 through 16. That would be pretty conservative there, okay? So these are the values did, okay? Now, for these inputs, those were the outputs. Now, remember what makes it a function? For every input, how many outputs can you have? One and only one. It's like the bookstore line when you're buying chips. If they charge that guy in front of you for the same bag less than they charge you, you're not a happy camper, because for any input, you better have only one output. Now, notice here about 3 and 4 o'clock. Does that violate that? No. At 3 o'clock, you only had one temperature. When you're reading that thermometer at 4 o'clock in the afternoon, 3 o'clock in the afternoon, it's only going to be one temperature. But it can be that same temperature again at 4 o'clock. You can have more than one inputs for the same output. You can't have more than one outputs for the same input. That's the key. This is a function. Does that make sense? Okay? Now, the following is another way to express functions. Ordered pairs. Now, what do we mean by ordered pairs? I think y'all know this pretty well. 2 words there. What's a pair? 2. It's not a fruit. That's a different one, okay? And what does ordered mean? The order matters, okay? So with ordered pairs, you have a first coordinate, pair, one coordinate. That's the x value. Now, that's what they call it. It doesn't have to be x, but quite often it is. That's your input value. And the second coordinate, the y value, in this case, would be the output value. Okay? Now, remember back the first function we looked at, this one, your inputs were your r, your output were i's. It doesn't have to be x and y. It's whatever input and output is. Okay? Just a reminder. They focus in on X and Y. It doesn't have to be. Now, what does this mean? What does the curly Q? They call that a brace. What does the brace mean? A set. That means a set. What does parentheses mean? Ordered pair. Okay? A set of ordered pairs. And what are those? 1, 9. Sound familiar? 2, 13. 3, 15. 4, 15. 5, 12. 6, 10. That's the same set as we had on our mapping. Okay? Exactly the same set. Input was time of day. Output was temperature in Celsius. Right? Okay. So here's another way to express it. And we haven't got the graphing yet, but we'll get there. So here's the characteristics of a function that maps from set A to set B. Each element in A must be matched with an element in B. Okay? If it's in the domain, it has to have an element in B. Here, we didn't have any stray values you didn't match. Okay? So everything in here. But remember, you don't have to use all the ones in B. Okay? Some elements in B may not be matched to the element in A. Yeah, we saw that. 1, 2, 3. No, 1, 2, 3. Well, goodness gracious. Up to 8 were not mapped. 9 wasn't mapped. 10 was. 11 wasn't. 12, 13 were mapped, but then 14 and 16 and on beyond that were not. So you don't have to use everything in B. Okay? You have to use them all in A. 2 or more elements in A may be matched to the same value in B. Like 3 and 4, both match to 15. But an element in A cannot be matched to more than one element in B. Can't happen. An element in A, the domain, cannot be matched with 2 distinctly different elements in B. If that's the case, not a function. Relation, sure, but not a function. Just like you can't read that thermometer and get 2 different temperatures at the same time. Okay? So here's 4 common ways to represent the function. Verbally, okay? You're my input set. You're the domain. Your birthdays may be the range, okay? You think that's a function? It could be, but guess what? What if 2 of you have the same birthday? That's fine. Yes, none of you have 2 birthdays, though, do you? Okay, so you see, that is a function. Okay? Now, so that's a verbal by a sentence that describes how the input variable is related to the output variable. Numerically, you can do that in a table or a list of ordered pairs. Now, we haven't shown a table yet. We're going to do one in a minute that's just like a set of ordered pairs. One column is your X, one column's the Y. One column's input, one column's output. Y'all did this when you graphed, right? The chart ends here, right? Okay. There you are. Okay. Good deal. Anyone else come in since I called roll? Okay. Graphically, this is the one we haven't shown yet, but we're going to. Can I get your name, please? James. Graves? Okay, what do you go by? James? Okay. Okay, this is your first time here, right? Okay, welcome. Now, sorry, going to have to take a quick time out. The syllabus I went over first day of class, and it's also on Blackboard, okay, under content. So is the research paper instructions. I went over that in class. It's on Blackboard under content. My locator card, we didn't go over it in class, but it's in Blackboard now. Also, all the PowerPoints are in Blackboard under content that we'll use all term, probably way more than we'll use all term. And also I've put several sites under content in Blackboard that you might find useful for the class. Other students have, or I found them independently. Okay, I'm also have recorded, will continue to record all the classes on this new program for me anyway, called Screencast-O-Matic. And so far, it's given me a lot of difficulties. None of those are out there yet. Hopefully this afternoon they will be. So you'll be able to go back and listen to both of the classes last week and what you missed so far this morning. Okay, so third way to represent a function, graphically. Okay, and graphically, we usually use the Cartesian coordinate system. Let's just give a little bit of background here. What do we call this line here? Okay, everybody calls it the x-axis. Remember, it doesn't have to be x. So I call it the horizontal axis. That's a little more generic, okay? And what do you think would go on the horizontal axis? The domain, the input values. That's where you find those. And then, what does this axis, what's that called? Vertical. Y'all are good. Vertical axis, or often called the y-axis. That's where your range goes. So you find the domain value, 1. What was that value? 9. There it would be. 1, 9, 2, 13, whatever. You would find the values there. So that would be graphically by points on a graph in the coordinate plane, which the horizontal axis represents the input values, domain, and the vertical axis represents the output values. And then finally, algebraically, and we did this at the very beginning, by either an equation or something like that in 2 variables. I is equal to 1,000 R. That was one we had at the very beginning. So 4 different ways, and this one actually has a couple of ways within it to express a function. Okay. Now, I don't mean this to be confusing, and don't let it be, but let me just go back and point something out. This set, which was also the mapping set, this is called a discrete function. Now, you don't have to know that for sure. The book doesn't talk about it. But what that means, it only has certain values. You didn't sit there and record. Now, actually, when I was in the Navy, I was on an ammunition ship. And it was maybe a little bit important that the holds where we kept the ammunition, the air conditioner worked there, okay? It was just a little bit important, because you didn't want those really overheating a lot, right? Okay, so actually we had in the most sensitive of those holds, where the most sensitive ammunition was, we actually had a strip chart recorder that recorded the temperature continuously. This we're not. We're only looking every hour. That's a discrete function. This would be points, like I was showing here. It would be this point, that point, that point, that. Those would be points. That's the discrete function. That strip chart recorder gave the temperature at it was a continuous function. So I wanted to mention that because your graphs could be discrete or they could be continuous, okay? So we'll talk about that a little bit later, okay? Now, to determine whether a relation is a function, you must decide whether each input value is matched by exactly one output value. Has to be a function. When any input value is matched by 2 or more output values, the relation's a relation, but it's not a function. Okay. Now, they've hit that all over. Here's example 1. Now, see, a few of you have books, but not everybody. This is on page, that's right. I'm not, okay. About the middle of page 36. Determine whether the relation represented here represents y as a function of x. Okay? A, this is a sentence one. The input value x is the number of representatives from a state, and the output values is the number of senators from that state. Is that a function or not? What did I hear? I heard a no. Why not? Say again?
More than one output.
Really? Okay. Does Alabama? Does it fit as a function or not? That's our state. How many representatives do we have? Now, we're talking about national, okay? I don't know. What are we? 8, 7, or 8? Something like that? I believe so. How many senators we got? 2. We don't have 2 and 7? 2 and 14? No, we only have 2. So for every input value, x, 8, we only have one output value, 2. So surprisingly, this is a function. Okay? Some states, like Wyoming, only 1 representative. How many senators they got? 2. Okay? So for that state, Wyoming, 1 representative would have 2 senators. Alabama with 8 would have 2. California with, I don't know how many, they only have 2. Guess what kind of function that is? It's a constant function. It never varies. No matter how many representatives you have 2 senators. Okay? So, for every input, there's only 1 output. The output is 2. Okay? Strange but true. That's a weird one to give you first example in that we do. You know, it is a weird one. If it was the other way, no. You just don't have any states with negative representatives, but you could have, say, the number. Okay. Let's go back to our thermometer example. We started at 1 o'clock. Okay, that was our first value. What would 11 o'clock have been on that scale? It was 2 hours before we started, so that would have been a negative 1. Okay, and it was the temperature then. You know, it may have been cooler than 9 degrees or somewhere. So you could have negative. Yeah, it can cross that. I know what you're thinking, though. You're thinking the vertical line test. Yes, he's ahead of us here, but that is an important point. Okay, the y-axis is a vertical line. If at 0, there weren't 0 representatives from anywhere, but if at time t equals 0, like 12 o'clock noon, that same day we were talking about, you had a time. But if you had more than 1 temperature that day, it wouldn't be a function. 1, still a function. And if there was negative, 1, still a function. So what you're thinking is vertical line test, not the y-axis, vertical line test. Okay, I think that you're thinking. Here's one in a table. This is a lot like ordered pairs. Is this a function or not? Why not? Given 1 input, 2 outputs. Can't happen in function. Is a relation, not a function. And this would fail the vertical line test if you graphed it. Okay? The rest of those would be fine. In fact, if you left that off, that would be a function. With 2 values of 2 yielding 2 different values of output, can't be a function. How about C? There's a graph. Is that a function? Okay, yes it is. Okay? Because what are your inputs here? This one crosses the y-axis, so this is a function. Negative 2 is an input value. What's the output? 3. Okay, what's another input? Negative 1 is output. Okay, another input? 0. What's its output? Another input? What's the output? And finally? 2, 3. So your domain is a set of what numbers? These are discrete. Negative 2, negative 1, 0, 1, and 2. Those are your inputs. That's your domain. What's your output on this one? Negative 1, 0, and 3. Yeah. Those are the only ones you use. Your range could have other values like 1 and 2. They could be in the range, but they're not used. Okay. So there we have our domain and range of that. That is a function. And, jumping ahead, every vertical line crosses at most 1 time. None of the vertical lines cross twice. The function doesn't cross the line twice. All right. So, here are their solutions. The first, the vertical description does describe y as a function of x, regardless of the value for x, whether it be 1, 8, or 23, or whatever, the y value is always 2. Such functions are called constant functions because they never vary. Okay, constant function. Okay? We'll be naming functions all sorts of things. The table does not describe a function. You gave the reason exactly. The value 2 is matched for 2 different outputs. Can't happen in a function. So here's the key. When you have it as a table or a set of ordered pairs, look at the first values. If you see a same first value mentioned twice, that's suspicious. Look at the second values if those are different, whether it's in ordered pairs or tables. If they are different, not a function. Okay? Graphs, vertical line test. We haven't gotten there yet, but you did. This one, the words sometimes are harder to see, but we'll figure it out. Okay? So we got the table. And the third one, the graph does describe y as a function of x because for every input value, there's only one output value. Okay? And there were only 5 inputs, really only 3 outputs. That's fine. You can use the same output twice. You can't use the same input twice to get different outputs. All right. Now, representing functions by sets of ordered pairs is common in discrete mathematics. I forgot this book actually used that term. Can I get your name, please? Okay. Let me find the roll then. Here we go. Chantel. Got it. Anyone else come in since I called roll? Okay. And by the way, I saw it posted today. I may have gotten to it, but I haven't seen it on my email. But Pell Grant disbursement is the 1st, which is Friday. Is that right? Yeah.
Do you know any information about that? Like, how does it work here?
Is that what?
Do you know any information about that? How does it work here?
How does it work?
Okay.
Okay.
I know most schools have stipulations like show you have to go to 5 classes first, be on the roll for all 5 classes before they give you a program.
Okay. Okay. I think I understand your question then. Okay. What we have to do is submit attendance, and we've done so. And if you are in a class and your instructor didn't submit attendance, you're not going to get a check because they can't show that you're there. So you don't have to prove it. The instructor was supposed to have done it. I recorded the attendance, so anyone who today was the first day, don't expect anything yet because that was done. I submitted that on Friday. Okay, you were here last week, weren't you? Yeah. So yours would have gone in for me. I can't tell about your other instructors, but they are on us like crazy to get our attendance in by Friday, and then even Friday and Saturday classes, they really harp on them too. So that's how it works here. Okay, I was thinking you meant how do you pick it up and stuff like that. All right, so it's the same type thing. You have to show that you've been here, and that's through attendance. We record that. It's all done. We record on the computer, and that's all tied in with financial aid. If there's no state of attendance, no check. Okay. All right. So that's discrete mathematics. When you have sets of ordered pairs, that's discrete. Each value has one. In algebra, however, it's more common to represent functions by equations or formulas involving 2 variables. And in this case, y is equal to x squared. Is that a function or not? Yeah, y is x squared. Give me an x. I feel like a cheerleader. Give me an x. 0. What would your y be? 0, 1, and only one answer. Whatever x you give me, there's only going to be one y, right? You can't give me a number that when I square it, it's going to give you 2 numbers. We can. You can? Okay, good. Okay. How about -1? What would that give me? X is -1. Y would be 1. If you gave me x equal 1, what would y be? 1. That's okay. As long as for any given x, there's only one y, you can have more than one x's that give you the same y. That's okay. That is a function of x. Now, this typically would not be counted a discrete function. Now, the numbers I called out, you called out, were all integers. But guess what? You could have given me 0.3, and 0.3 squared would be 0.09, okay? You could have given me pi, and pi squared would be pi squared, whatever that is. You could give me any number in the world that would give you an answer. This would be a continuous function. We'll talk about those later. This represents the variable y as a function of the variable x. In this equation, x is the independent variable. That's why I say, give me an x. You can choose any x in the world, okay? Most of the time. That's the independent variable, y dependent. Because once you give me an x, then that y depends on what value that x was, okay? Now, we're going to do this a little bit later, but let's do. Since you can give me any number in the world, what do we say the domain of x is? All real numbers, okay? Integers, fractions, decimals, rational, irrational, doesn't matter. All real numbers, okay? Now, in this case, what's your range? Is it all real numbers also? Why not? Okay, y'all gave me a few examples. When x was 0, y was 0. When x was 1, y was 1. When x was negative 1, y was 1. Say again? Only positive numbers. You can't give me an x that when you square it, you're going to get a negative number. Not in the real number system. Don't go to the complex numbers. You can't do it there. The real number system, you cannot. So if the domain is all real numbers, your range is not all real numbers, it's all real numbers greater than or equal to 0. In other words, all positive real numbers. That's beside the point here. But x is the independent, y is dependent. So what you put on the horizontal axis is independent. What the values here depends on what that value was there. Okay? So that's why we call them that. Now, the domain of a function is a set of all the values taken, I don't like this, taken on by. That's two prepositions in a row. They wouldn't score very well in the English class, would they? No. Okay. By the independent variable x, the range of the function is a set of all values taken on by the dependent variable y. Okay? We've already said that. Here it is again in terms of expressions, algebraic expressions. Okay? When using an equation to represent a function, it is convenient to name the function for easy reference. Fred, Sally, no, that's not what you usually do. For instance, if you know that the equation is y is equal to 1 minus x squared, that's an equation in two variables, right? Is it a function? Why not? Is it? Give me an x, any x in the world, you're only going to get one y, right? So yeah, that's a function. That does describe y as a function of x. So that's an equation. But suppose you wanted to name, let's see, what do we call the function? What's your favorite input variable? Output is y. Okay. The favorite name for a function is f. Function, f. Okay. You can name it anything else. It doesn't have to be f, but that's what their fallback. That's their default. Most of the time is f. Then you can use the following function notation. If your input value was x, your output, what were we calling it? Y. So here is the most important thing to remember about functions throughout the course. And it's not that hard. Y is equal to f of x. If you remember that, you've got it knocked. Okay? That y is your f of x. What we were calling y, we're now calling f of x. So here, instead of y is equal to 1 minus x squared, this f of x is equal to 1 minus x squared. And you think, why? It's easier to write y than f of x. But, have any of you done any computer programming? I'm guessing probably not, but some of you may have. In computer programming, in fact, I actually had an adjunct instructor say, why do we focus so much on function here? I said, and in computer programming, what you do, if you want to do this operation repeatedly, you just name it as a function. And when you call that function's name, your computer program just jumps to that function, does it, and sends you back an answer. You give it in that input, it gives you back an output. And in computer, that's what you do. And then in calculus, it's also the same thing. We deal with functions. So, whereas before this was an equation, now it's called a function. There's really no difference. If you can just remember y is equal to f of x. Our dependent variable is equal to your function. So, now, remember that. The symbol f of x is read as the value of f at x. Remember, f is that, I gave the example last time of that meat grinder, the sausage grinder. You put the inputs in, that's your x's. You turn the crank and it turns those inputs into an output. Okay? So it's the value of that function, whatever that function is doing. That one function was just squaring the number. You feed in a number, it squares it and spits out the answer. That second one was, you feed it a number, it takes the number 1 and subtracts that square from it. Okay? That was a different function. Okay? So the symbol f of x corresponds to the y value for that given x. So you can write, here it is in writing, y is equal to f of x. Remember that. That's the most important thing in functions to remember. The output value is your function. Keep in mind that f is the name of the function, like Fred or Sue's or something like that, whereas f of x, not f, the f of x is the value of the function at that value there, at that variable x, that value for x. For instance, let's throw another one down here. Okay. Here's another function. This is different. They called it the same thing. This is like, I don't know if y'all remember the old sitcom that Bob Newhart was in, and they were running in, and this guy who did work, he'd come up, and here's my brother Daryl and my other brother Daryl. You know, it's sort of like this. We use the same name over and over. We really shouldn't. Every time you really should name your function something differently. But here's our new function. We're not using the others, so this is our new function, f. Okay? Also, who is the old boxer? He named all his kids with the same name. I don't know. Anyway. F of x is equal to 3 minus 2x. There's a function. What is it? You start with the number 3, you subtract twice whatever the input is here, and you get the new output. Right? So let's do it. Here's f of x is 3 minus 2x. How in the world are you going to figure out the value for f of negative 1? Plug it in, just like lathe. So every center you see an x here, you put a negative 1. So what do you get there? 3 minus 2 times negative 1. Minus 2 times negative 1 is positive 2. 3 plus 2 is 5. Absolutely. How about 0? That's my favorite. That's why I like it. No. Okay. What's this one? 3. 0. That would be 3. We go 3 minus 2 times 0. Minus 2 times 0 is 0. 3 minus 0 is 3. Okay. How about 2? What's f of 2? Okay, that would be 3 minus 2 times 2. Minus 2 times 2 would be negative 4. 3 minus 4 is negative 1. Perfect. Y'all are good. So you see you can plug in any value in the world. So your domain would be all real numbers. And in this case, what would your range be? All real numbers. Okay, you may not know that yet, but it indeed is true. To find that these values, substitute the specified input value, this, that, or that, into the given equation. This is replacing the x here, let it replace the x here. That's how you evaluate a function. Pretty straightforward, huh? All right, and here they show it. Got the same thing we did for x, negative 1, 3 minus 2 times negative 1 is 3 plus 2, 5. F of 0, 3 times minus 2 times 0 is 3 minus 0 is 3. F of 2 would be 3 minus 2 times 2. Minus 2 times 2 is negative 4. 3 minus 4 is minus 4. Good. Although f is often used as a convenient function name and x is often used as an independent variable, you can use any other letters you want to. Okay? Now, I wouldn't use x of x. That's really confusing. Okay? So, and don't use x of y and y of x. You know, those are related. Okay? But use some function. And usually the functions are f, g, h, and those kinds of things, and the variables are X, Y, Z, and that kind of thing. But you can use any thing in the world. Okay? So here's f of x is equal to x squared minus 4x plus 7. Okay? Here's f of t is equal to t squared minus 4t plus 7. Are those same or different? They're really the same functions. Because it takes whatever you put in here, whether it's x or t, whatever you put in there, it squares it, it subtracts 4 times it, and then it adds 7. That's your function. Those are the same functions. Or you could even name it g. G of s would then be s squared minus 4s plus 7. Same thing. The g functions are the same as these f functions. The s's, even though we call x your independent variable, this is not, that sounds pretty important, independent variable. Guess what else it is? It's a dummy variable. Okay? It really is standing for nothing. You could put anything in there in its place. You could put a stick man in there, okay? And alpha stick man could be stick man squared minus 4 stick man plus 7. I mean, you could put anything you wanted to in there, okay? They all define the same function. In fact, the role of the independent variable is just a placeholder, and quite often, derogatorily, we call it a dummy value, okay? Now, consequently, you can put a gray box there, okay? Alpha of gray box is equal to gray box squared minus 4 gray boxes plus 7. Whatever you put in there, it's going to square it, subtract 4 times it, and add 7 to it. Function is defined by 2 or more equations over a specified domain. Okay, this sentence here should be on the next slide. It should not be on this slide. It has nothing to do with that. But whoever the slide person was, put it there. This is a completely new subject. Or not completely. A function defined by 2 or more equations, not just one equation, but 2 or more equations, over specified domains or portions of a domain, that's called a piecewise defined function. That should have been this slide. Here's the example, and this is example 4. Now, wait a minute here. We had example 1. I wasn't paying attention. We skipped example 2, 3, and 2 and 3. So let's go back, and let's see, where should we do? Oh, and by the way, there's a beautiful picture on page 37. Leonard Euler is how you pronounce his name. Swiss mathematician, really handsome chap here. He was perhaps the most prolific and productive mathematician in history. He wrote more, it seems like 700 articles or things on math, books and things. I mean, how he found the time, I don't know. But he, one of his greatest influences on mathematics was his use of symbols. He came up with this y is equal to f of x. Blame it on Euler, okay? Does anyone know the number e? What that is? It's the base of the natural number system. Guess who came up with it? Euler, named after himself. E for Euler, okay? I think that's what. He did a whole lot of stuff this way. He has several formulas just incredible. So he's a potential paper topic, by the way, or any one of the dozens of things he did would be potential paper topics. All right, so let's go back here. All right, this would be a good place to do this one. It's a slide we already did, and I should have stopped. Goodness gracious. Dr. Bryant used this, my computer, and somehow got this pen tied up in the cord. Unbelievable. A rat's nest. Okay. And I'm doing just about as badly. I can't get it loose. Here we go. Okay. One more twist. Several more twists. I think we got it free. All right. Free Willy. Okay. Here's example 2. Which of the equations represents y as a function of x? Here's number A. Let me change my... Okay. Have I written on the screen before in this? Okay, I thought I had, but just in case. This gets recorded too, that's why I'm doing it. Here's an equation. X squared plus y is equal to 1. Is that y? Can that be expressed as y as a function of x? That's the question. How? Okay. Solve for y. Exactly. Solve for y and see what happens. Well, someone said subtract x squared from both sides. And that gives me y is equal to, because these go out, 1 minus x squared. Guess what? What is y? F of x. You got it. Yes, it can be expressed as a function of x. Good. Okay, that one was easy. How about this one? This looks pretty similar. Minus x plus y squared is equal to 1. Can that be expressed y as a function of x? Okay, how would you do it? Solve for y. Good. So how do we do that? Second, add x to both sides. That's a good start. Okay, so that would give me, these go out. They've been dating. No, never mind. Okay. Y is equal to x plus 1. And now what? I've got y squared. I don't have y. Second, take a square root of both sides. And this would be y is equal to, but when you take a square root of both sides, what do you have to put in? Plus or minus the square root of x plus 1. Don't you? Because what's the square root of 4? 2 or negative 2. Because negative 2 squared is 4. 2 squared is 4. You have to put plus or minus in there. That gives us a problem, doesn't it, Houston? Give me an x. An easy one. My favorite. What's your name? Okay, 1 will do. Okay. All right. And 1 plus 1 is? 2. Square root of 2 is some irrational number, but it's 1.414, blah, 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 blah. But this is either plus that or minus that. You gave me 1x. Guess what? You got 2 y's. Shame on you. Okay? Not a function. That cannot be written as a function of x. Okay? So, this one can, because you can isolate the y without ambiguity, without having more than one value. That one cannot. Okay. I'm glad I caught that. That, to me, is one of the more important examples. I didn't put it on the slide set. Okay. And then evaluating a function, that would come right after this slide, I think. So let me do it here. Okay. Before this. Okay. Let g of x equal to minus x squared. Now, I can almost hear some of you saying, why is he so awkward up there with this? Well, I'm just awkward, but no, that's a plus 4x plus 1. Because I'm left-handed, I like to have the computer over here, my book over here, but then I found out I wound up being in the shadow and you can't see what I'm writing anyway. So I have to move this over. Somebody in my last class said, you're blocking the view, you're blocking the view. So, okay. Anyway, here's your function. What we want to do is find each function value. What is g of 2? How would you do that? Plug it in, plug it in. What would I do? Minus 2 squared plus 4 times 2 plus 1. And by the way, when you see a number written next to a variable, that means multiply. You don't write number next to number, that would be 42. That would be hard to see. You put that in parentheses. But here we have a dilemma. So you have to be very careful here. What is that answer to that first term? Okay. Any of you remember, please excuse my dear Aunt Sally. I don't know what she did, but please excuse her, okay? What does that mean? Parentheses first, we don't have any. Excuse exponents next before you do multiplication and division, and that's before you do addition and subtraction. what do you do first here? Exponentiate. So it's minus 2 squared, which is 4. Then you do, this is like in a subtraction